Good morning, class, and welcome to our next lecture in central carbon metabolism. Today, we're going to be talking about glycogen biosynthesis and its degradation. We're going to talk about how it connects to central carbon metabolism. So your body stores energy in a lot of different forms. Of course, we're quite familiar with how we store store energy in terms of fat and muscle proteins. Like there's immense reserves in our body there, maybe 80,000 or more kilocalories you have stored away of fat and 30,000 calories in the form of protein. But your brain runs on glucose, and most of our the energy that we need right away, ultimately for short bursts of energy, comes from carbohydrate metabolism. Now, if we break down the carbohydrates, you'll see that you have very little energy in your body in the form of glucose. So we have about 80 kilocalories around in your body. Now, that's a pretty substantial reserve compared to the amount of ATP that you have sitting on demand in your body, which is only 5 kilocalories. But we do have this reserve there in your blood. And then we have two larger reserves of carbohydrates. Now, obviously, this 80 and 5 here that we're talking about isn't enough to sustain any kind of real exercise. And if you were being chased by a bear, there would be a strong selective pressure to have another readily available source of carbohydrates. And you do. So you store it in your liver in the form of glycogen. There's about 400 kilocalories there, and you have another one in your muscles, about 1,500 calories there. Now, the difference between these two is that the liver glycogen can be mobilized and turned into blood glucose on demand, whereas your muscle glycogen is locked in there, and it's only used for energy or for exercise. So, what does glycogen look like? It's a 1,4-alpha linked glucose molecule. Both starch and glycogen have this as their sort of base chain. Now, they both of them also have 1,6 branches that we're going to learn about, but they have this start with this 1,4-alpha linked glucose chain, and then cellulose. The primary difference between that and wood is that cellulose has this 1,4-beta link glucose, which forms these very rigid structures that are hard to digest. So glycogen has this kind of base structure. And then so why do we have glycogen? Well, obviously we use this as our primary source of energy when we need to either maintain your brain, or when you're going to have to engage in short-term bursts of exercise. We use our glycogen reserves really extensively from that. So as I said, there's 80 calories in your blood, 400 calories available in your liver, and about 1,500 calories in your muscles. And so these are broken down as needed to support your physiology. And the way that this works is that the glycogen is stored up into these long chains that we just talked about. And these chains can be organized in a couple of different ways. If starch, or amyloid, it has this one long 1,4 linkage chain here. We don't store our glucose in this form. We follow this glycogen storage form, which has both this 1,4 linkages and also these 1,6 linkages. Amylopectin also has that, or starch also has these 1,6 linkages, but the primary difference between amylopectin and glycogen is just the rate of branching. And so my question to you is, why don't we store our glucose in this amylose form here, or this cellulose form? Well, the cellulose form is pretty obvious, like this 1,4 beta length chains are very hard to break down. It requires special enzymes to break them down, and they're not very digestible. So that's why we don't use cellulose. But then why don't we use something like amylose? And why don't we just store it as glucose? So the reason for that is that you can't actually store much glucose around because it starts to become osmotically impossible. In other words, there's a finite amount of material you can keep dissolved in your blood, and glucose is one of those molecules that contributes to osmolality. So by polymerizing it as glycogen, we can actually remove it from solution, and we can store a lot more of it than you'd be able to store as a free monomer. And then why do we store it here as this branched form? Well, this has a lot to do with how we degrade glycogen, and we'll talk about this in more detail in a minute. But we actually degrade it from the ends backwards. So, like from these far ends, we chew it up. So if we were to store it as amylose, for example, instead of as glycogen, then the rate at which you could break down and mobilize glucose molecules would be driven by the enzymatic rate of the enzyme. But when you have a whole bunch of different ends, you can have a whole bunch of enzymes operating it at the same time, all breaking it down and mobilizing it at the same time. So we store it as glycogen in this branched form because it allows the glucose to be mobilized very quickly if it needs to be. Okay, so glycogen is not just carbohydrate. There's actually a protein core to it called glycogenin. And then around it is this big nest of carbohydrates that's the glycogen itself. So it has this big structure. Now, like all sugars, glycogen has both a reducing and non-reducing end. This carbon 1 is always the reducing end, and then the non-reducing ends are the far side of the chain here. So as I mentioned to you before, the primary base structure of glycogen has got this 1,4 alpha-linked chain, but then it has these 1,6 alpha-linked branches that come off, and that's what gives it this sort of three-dimensional structure. So how is it actually synthesized in the body? It comes from a pathway that starts from glucose 6-phosphate. This is the same branch point we talked about before for the pentose phosphate pathway. It comes, glucose comes in, phosphorylated, turns into glucose 6-phosphate. And at that point, it has to choose, is it going to go down glycolysis or can it be committed towards glycogen synthesis? Now, obviously, this isn't happening in all cells, but in liver and muscle cells, this is an option. And the overall pathway is that glucose is converted from glucose 6-phosphate to glucose 1-phosphate. That molecule is converted into UDP glucose. We'll talk more about this in this very significant energy committing step. And then ultimately that UDP glucose is used to synthesize a growing glycogen chain. And then it can also be broken down following a similar kind of pathway. And we're going to talk about this pathway where there's glycogenolysis will be freeing the glycogen into glucose units. Okay, so overall, glycogenesis is the synthesis of glycogen. Glycogenolysis is the degradation of it. Talk about these each. Okay, so glycogen is synthesized by this enzyme glycogen synthase, and it grows from this core that's sitting at the reducing end towards the non-reducing end of the molecule. So it gets extended in the non-reducing direction. And this happens iteratively where we add units on, add units on, and add units on. And eventually, a whole bunch of these units will be displaced and then move to a 1,6 position, and that's this branching enzyme. And that branching enzyme is what gives us this very complex structure. And it also allows the glycogen to be synthesized faster than the rate of a single glycogen synthase enzyme, right? So for the same reasons that we keep it branched, because we can synthesize the glycogen faster and we can break it down faster. And this branching enzyme is what does that, that it creates that structure. So the actual chemistry goes for like this, where we have the glucose comes in as glucose 6-phosphate. There's an enzyme, phosphoglucose mutase, that transforms it from this 6-phosphate form to this 1-phosphate form. As you recall, a mutase enzyme is a transformation where the phosphate will come off the molecule, it'll go onto the enzyme, and then it will come back in another position. So it is not just an isomerization, it is a physical rearrangement of the covalent bonds, right? So this molecule here then engages in one additional step where it reacts with UTP. UTP, uridine triphosphate, is very similar to adenosine triphosphate, can be used in some biosynthetic reactions. And the thing about this one is it actually releases pyrophosphate. So two phosphates go into making this, so two ATP equivalent. So it's a very significant energy commitment step. We're already starting with a phosphorylate intermediate, and then we add the equivalent of two additional phosphates in. So 3 ATP have gone into the making of this UDP glucose. Okay, and at that point, then this molecule is ready for synthesis. Then you can imagine if you're going to have this 1,4 linkage, you just count down from here, this carbon 1, 2, 3, 4, and you can have a nucleophilic attack of those hydroxyls on this position. This is a leaving group, and you end up kicking out UDP, uridine diphosphate, as a leaving group. Okay, and that gives you a growing glycogen chain of this 1,4 glycosidic bond. And the overall equation looks like this. Now you can actually break glycogen down in a single step via hydrolysis. And this happens in your mouth. There's an enzyme in your mouth called amylase that starts to digest starch as soon as it gets into your mouth. This is why we really like highly refined breads. This tastes so good. The reason why is that you're actually mobilizing glucose in your mouth, which tastes great, and this is possible via hydrolysis reaction. So this is catalyzed by amylase, but you have a nucleophilic attack of water here at that same position, mobilizing this mobilizing these bonds. So and this occurs internal to the chain. Now, that's a really wasteful strategy for breaking down glycogen. And if we were to do that, we would be losing the equivalent of 3 ATP for every single molecule of every monomer that we release in glycogen. And so your body has a shortcut that allows it to save at least 1 ATP equivalent of energy. And the way it does that is by having, instead of having a hydroxyl as a nucleophile, it actually uses a phosphate as a nucleophile. And then this reaction, which is what's occurring in your liver and your muscle, is called a phosphorylase reaction. So the nice thing about the phosphorylase reaction is after you undergo this nucleophilic attack, this transformation, you end up regenerating glucose 1-phosphate, which, as you recall, was the first step in glycogen biosynthesis. So by doing that, you've only lost 2 ATP in the round trip from synthesizing the molecule and then bringing it back, rather than 3. In other words, we're regenerating the energy equivalent of the glucose 6-phosphate molecule that went into the pathway originally. That can go back and equilibrate through phosphoglycerate mutase, just the reverse of the synthetic reaction that we saw earlier, to make glucose 6-phosphate, and then that can enter into glycolysis, or it can be released back into the blood in the case of the liver, and then it can move around in your body. Now, importantly, this last step here of taking it back to glucose and secreting it into the blood, that's something that the liver does, but the muscles do not. Okay. So breaking down of glycogen follows the same pattern that we saw here for the synthesis, wherein we have a breakdown from all the individual endpoints here, starting from the non-reducing end and moving towards the reducing end. Eventually, it will leave this chain of 4 remaining glucose moieties here at the end of this chain, which is the farthest that the phosphorylase enzyme can move, glycogen phosphorylase enzyme can move. And then a debranching enzyme or transferase will move those 4 remaining enzymes off onto the endpoint to allow this additional catalysis to occur. Now, when it does that, it actually isn't able to remove this final 1,6 linkage that's left, and that last 1 molecule of glucose actually gets hydrolyzed off. So for every branch that you have in your glycogen chain, you'll end up losing 1 glucose molecule that's going to be hydrolyzed rather than remove via phosphorylase reaction. Okay, so there will be one equivalent loss of an ATP for every branch. Okay, so here is our overview of the reactions that we talked about before, with glucose coming in, being synthesized into glycogen, either via the glycogen synthase reaction or the glycogen phosphorylase reaction is broken back down. Of course, this phosphorylase reaction bypasses these two steps to make glucose 1-phosphate. But this is how the chemistry works. Now, what is the process that prevents these two pathways from happening at the same time? You can imagine if you're hydrolyzing ATP and driving this reaction forward, that would be energetically favorable for this thing to be converted all the way into glycogen, then just converted right back into glucose in a big futile cycle. To prevent that from happening, we actually have really extensive both covalent and allosteric regulation of glycogen phosphorylase and glycogen synthase. So glycogen phosphorylase is one of the master controllers here, is one of the main control points here for regulating the breakdown of glycogen, and is a really classic example of how there are multiple layers of both allosteric and covalent effectors that change the activity of this pathway. Now, this enzyme has two states, a relaxed state and a tense state, so T and R. These are conformational states of the enzyme. Now, it's active in its relaxed state, the R state. R, relax, is active. T state is the inactive form of this enzyme. When you're tense, you can't get anything done. Yeah, so that's the same with the enzyme. So this R and T conformer can be reinforced by phosphorylating the enzyme. We're going to talk about how that works. So a phosphorylase A form of the enzyme tends to lock it into this R state, active state, and a phosphorylase B form tends to lock it in this T or inactive form. We'll talk about how that works. So in the case of phosphorylase B, there are the enzyme is most happily in its T state. Now, both the B and A can exist in both T and R states, but the phosphorylation tends to drive the enzyme to favoring this relaxed isoform, and the dephosphorylation tends to drive it towards favoring this tense or inactive isoform. Okay, so this phosphorylation on the enzyme is accomplished by an enzyme called phosphorylase kinase. That means it's an enzyme that's putting a phosphate on the phosphorylase enzyme. Okay, and these phosphates then lock it into this active form. And when that phosphate is removed, it can go back to the inactive T state. In other words, there are two forms, a T and R. And the phosphorylation event tends to drive the enzyme towards one state or the other, where the phosphorylated state is locked towards the active form and the dephosphorylated state is locked towards the inactive form. Yeah. So this is only one layer of regulation on this enzyme. So on top of this covalent level of regulation of the enzyme, there's also allosteric regulation in the enzyme. In the liver, glucose molecules will bind to the phosphorylase enzyme and shift it towards the T state. Okay, so this is by default, the liver lysozyme is normally in the phosphorylase A form or D. And in this state, if it binds glucose, it tends to shift it here towards this inactive form. And that makes sense. Glucose is the product of the end product of glycogenolysis. So having extra glucose around tends to encourage the enzyme to stay in its inactive form. And similarly, in the muscle, which is normally in its phosphorylase B form in the muscle, the binding of nucleotides will shift it between the T and the R state, with AMP shifting it towards the R or active state, and ATP or glucose 6-phosphate shifting it towards the T or inactive state. Why is that? It's because the AMP is a signal of starvation and in the muscle. And so when the muscles are starved for energy, they want to trigger their glycogen phosphorylase to release more glucose. And when there's plenty of energy around, they want to tend to turn it off. So this allosteric layer, a layer of regulation, moves it back between the two forms. Now, why do we have an A and B form at all? Why not just do everything according to allosteric regulation? Well, the reason for that is that in the effect, let's talk about what the effect that has. In the A form, you'll see that it is quite, or in the B form, the enzyme is very responsive to allosteric regulation. But in the A form, it isn't. It's less responsive to allosteric regulation. Why would that be useful? The reason is that not everything that this enzyme is doing is responding to the microenvironments inside the cell, glucose levels or glycogen levels inside the cell. It also has to respond to physiology. For example, when a bear is chasing you, you've got to respond, and your body responds by firing a pulse of adrenaline or epinephrine. And that adrenaline or epinephrine needs to signal the body to start turning out glucose molecules in preparation for major activity, irrespective of what's happening inside the cell. And maybe there's plenty of energy there, but it knows it's going to need a lot more soon. Similarly, in the liver, there's states where, the liver cell itself might have plenty of energy, but the body is depleted in glucose. And so the body needs to tell the liver via glucagon to secrete glucose via glycogenolysis and gluconeogenesis. So this signal is actually passed to the body via these glucagon epinephrine receptors here. And that goes through a signaling cascade that's ultimately signaled through the cyclic AMP. So what happens is the receptor binds, it triggers the movement of this GTP-bound protein to adenylate cyclase, triggering the cyclization of AMP to cyclic AMP. That actually binds to and stimulates protein kinase A to move to its active form. Protein kinase A then phosphorylates phosphorylase kinase, turning it into its active form. And phosphorylase kinase is ultimately the enzyme that phosphorylates phosphorylase B, converting it into this A form, which is the active form of the enzyme that breaks down glycolysis. Protein kinase also phosphorylates glycogen synthase from its A active form to its B inactive form. And then, so this process stimulates glycogen breakdown in the presence of insulin, or I'm sorry, glucagon or epinephrine. So the different tissues have different roles. So in the liver, when glucose levels are low, glucagon or epinephrine are secreted. Glucagon in the case of low glucose levels, epinephrine in the case of, the bears coming. And both of these things stimulate the breakdown of glycogen via this mechanism we just talked about, and the secretion of glucose to the blood. Okay? In the muscle, something different happens. Epinephrine triggers the conversion of glycogen into glucose 6-phosphate, which is then committed into the central carbon metabolism. Okay? So they have two different roles, and respond to, and then can respond to either physiological or intracellular responses using this layer of allosteric and covalent regulation. So there's also regulation of glycogen synthesis in addition to glycogen breakdown. That's regulated through insulin. Insulin has its own signaling cascade with IRS, insulin receptor substrate. It gets phosphorylated, ultimately leading to a protein kinase that does similar activation of glycogen synthesis. Okay, glycogen synthase A is the active form, and insulin ultimately triggers this. So I think one of the main take-homes of today's lesson is that we use glycogen as a way of storing carbohydrates, and that need serves both intracellular physiological or intracellular energetic needs as well as whole body physiology. And so these multiple layers of regulation that we learned about today serve both those functions. And yeah, from today, you should be able to say, why is glucose stored in the form of glycogen? This is because of osmolality. And because its structure enables the fast release of glucose. And we have another question is why, why is glycogen branched, and how does the branching and debranching work? This is to enable, the rapid synthesis and breakdown of glycogen. We talked about the reactions that we went through. We talked about how they differ from amylase, particularly in respect to energy. And we talked about the regulation of this phosphorylase and synthase, particularly with the phosphorylase, and how it occurs through both this covalent modification enzyme with phosphorylation through allosteric activators and through hormonal activators. Yeah, and that's all for today. And I hope that this will bring you to a new and fascinating understanding of how glycogen phosphorylase helps you regulate your carbohydrates and helps you store energy and release energy according to what's going on in your body.